Hey, today we're going to talk about 4.4, Earth's atmosphere. So take a moment, check out the Enduring Understanding, look at the learning objective, pause the video, review the essential knowledge, and set up your Cornell notes. So the Earth's atmosphere is composed of different layers, and the closest layer to the Earth's surface contains gases with the following percentages. The most prevalent gas in the Earth's atmosphere is nitrogen, and nitrogen is present at the Earth's surface at 78%, roughly 80% if you can remember that, but it is by far the highest composition. And this nitrogen is not available for us to consume. It has to be fixed either biotically or abiotically through the actions that were described during the nitrogen cycle. The oxygen would not be at 21% if we did not have photosynthesis. Oxygen is very highly reactive, so it will definitely react with a lot of metals and other materials in the biosphere. So the amount of oxygen is only at 21% because of the high amounts of photosynthesis that occur. And a lot of the oxygen comes from the phytoplankton in the open ocean through photosynthesis and from the photosynthesis of the conifers in the boreal forests or the taiga. We also have around 1% of argon. Argon is a noble gas. It is inert. It does not react. But we have just about 1%. Now, water is very variable in the amount that it exists in the atmosphere, and that's because of the hydrologic cycle. The reason that water is included is because if the water vapor content is high enough, it is a high level of relative humidity, and that means that it can impact the overall surface temperatures because water has a very high holding capacity. On days when it's really humid outside, it might be 85 degrees, but it feels like 100 degrees because of humidity. The reason it feels so hot is because the water is absorbing that excess solar energy. And finally, I put CO2 in here. It is definitely not the fifth most prevalent gas. There's other gases that are found in higher concentrations. However, we talk about CO2 so much. CO2, global warming, climate change, carbon emissions, all of this stuff. Carbon dioxide is bad, but as bad as we make it sound, it has such a small portion of the Earth's atmosphere. But that little small portion does have a big, huge impact. And this 0.04% is actually equivalent to 400 parts per million. The actual level is above 400 parts per million currently. There are other trace gases that exist, but the ones you really have to know are nitrogen, oxygen, and just know that argon is third. Okay, so when we're considering the Earth's atmosphere, we will typically be looking at the temperature and the altitude. The temperature is on the x-axis along the bottom, and the altitude is on the y-axis. And altitude just means how far from the Earth's surface we are moving. So just to look through this, if you can't see, we exist right here. This is basically like room temperature or ambient temperatures at the surface. And as we move to the left, we have very cold, I put ice cube there, and here we have very hot. So this is what it would look like. When we start at the bottom, we have the troposphere. This is the densest layer of the atmosphere, which is why all of the gases are pretty much found here. All of the weather that we see on the surface, all of the weather occurs here. There is a slight exception. There is something that occurs in the polar regions in the stratosphere. Who cares about that right now? All weather occurs in the troposphere. Okay? Later on in the year, at the very end, there's one tiny little thing that happens in the stratosphere, and it's very only dealing with one little thing. So for our purposes right now, all the weather occurs in the troposphere. And at the surface, it's going to be warmer because the Earth's surface is very dark and it absorbs all of that solar radiation, so it heats up the Earth's surface. As we move farther up, it will cool off and it will become quite cold actually when we get near the top of the troposphere. And this is because there are fewer water molecules, there's fewer carbon dioxide, there's fewer molecules to absorb that sun's radiation, and doesn't hold the heat. Okay, so in between the troposphere and the next layer above it, we have the tropopause, followed by the stratopause and the mesopause, and you don't really have to understand what that is. There's just tropopause is at the top of the troposphere. It's just the division between the two. There's nothing special that happens there. I just wanted to point that out because it is on this diagram. Now above the troposphere is the stratosphere, and the stratosphere is known for the ozone layer, and the ozone layer is found near the bottom of the stratosphere. So what is happening is the ozone is absorbing the sun's radiation, and it is redirecting that radiation. It's absorbing it, and some of it's being sent back to space, some of it's being sent back to Earth, some of it's being transferred around in the stratosphere between the ozone molecules. So the temperature of the stratosphere actually rises because there is so much solar radiation coming in. Here the solar radiation, it is the temperature is a lot lower because the solar radiation is being absorbed by the ozone layer. Now once you get to the mesosphere, that's the next layer up, the tendency is for the temperature to cool, and most of the meteors are burning up here. So outside of the mesosphere, there's fewer and fewer atmospheric particles, but in the mesosphere the density is starting to get a little bit thicker. That provides friction to these meteors that are entering the Earth's atmosphere, so these meteors will burn up, and this is where we see all of our falling stars and meteorites. That's all you really need to know for the mesosphere. Moving on, we have the thermosphere, and the thermosphere is going to absorb X-rays and ultraviolet rays, and it will charge up the particles in the atmosphere, and these particles can release light when they go from excited state to ground state, and they release that in the form of light, this energy, and it's called aurora borealis in the northern hemisphere, northern lights. It's also called aurora australis in the southern hemisphere, and that's southern lights. If you want to see the aurora borealis, I used to be able to see them, not as vivid as you see in pictures, but I used to see them looking out our front yard in the summer. I could see them. It was kind of a faint little green little dancey thing, but I never saw big ribbons in the sky like you see in pictures. But if you go to Iceland, northern Scandinavia, parts of Canada, Alaska, Russia, you'll see beautiful displays of aurora. And finally, beyond the thermospheres, we have the exosphere. And all you need to know about the exosphere is it's basically outer space. It's where the atmosphere is merging with outer space. And when we had our, there was some billionaires that went to on their little space trips recently. I think they were about 60 miles out off of the Earth's surface, so that would have put them up into the thermosphere. I don't even think that they went out into the exosphere. But the exosphere is far beyond the thermosphere, so this graph would be a lot taller. But knowing where the exosphere doesn't come up on this test, so I didn't include it. There was basic information in here. I hope that it was informative for your FRQ practice. This is an example of a graph that you would see. I want you to describe the temperature change in the stratosphere as the altitude increases. So please take the opportunity to complete that right now. I thank you for your attention. I hope that this was informative. I will see you soon.